And welcome back. And we're in the last part of chapter 4 here. And then honestly, I think we'll probably skip chapter 5, kind of, it's focusing on more kind of the swept wing technology, and we'll probably jump ahead into chapter 6, into the kind of the details on the supersonic. But this section is on supersonic. And so, we've talked about in supersonic flight, the, wave drag, right? And honestly, there's a volume portion of it. So just a straight up drag, like you're plowing through this much air, it has this effect. And then there is also a lift component to that drag. So same sort of thing. As you are, have positive lift, CL, you have an extra component there. The wave drag increases that term. And so, we'll kind of talk through all of that in a second. But in the end, what you end up doing, right, as we kind of march forward in these chapters, is going to get less and less on theory and more on like measured results, analytical results, graph, things like that. And so what ends up happening, if you take a look at your drag coefficient, and this is for like a given aircraft size. And so this curve in Kuchemann was actually, okay, I need a CL of 0.1 and I'm at a Mach number of 2. And so what you can think of here as this is beta S over L. And again, beta is the kind of the shock angle. So beta SL over 1 would be wave rider, like the shock is attached to this aircraft. And so let's put that down here, 1.0, where the shock is attached and your lift would go up if you needed it to be. But what you end up seeing is that across all wing sizes, and so really what you're doing here is you're changing the size of your wing. So we can think about it, this x-axis, you could draw this curve as wing loading. You could draw it in terms of size. It's helpful to frame it here because of some interesting conditions. And so you're going to have a good chunk of this drag be just friction, right? And so it doesn't matter how big your wings are, if you will. The friction is just the same. The friction is going to go. The total friction will go up with the size of your wing, but it's already accounted for. This is because the drag coefficient is drag divided by dynamic pressure and the area of your wings. So the increase of friction with wing size is accounted for. So from a coefficient point of view, it's just the same. Your total ends up having some version like that, for which as you draw like this, there's kind of an increase here. It kind of calls out this portion due to the kind of a thickness effect, and then this portion due to kind of lift and wave, and then the rest left of this is sort of just the lift vortex drag, so the kind of the standard induced drag that we're thinking of. And so in any kind of given configuration, you would say plot this, and maybe Mach 2 is your cruise speed, and CL of 0.1 would be the amount of lift you need given you're trying to carry this vehicle size. You have some rough estimate of the vehicle size. And so that's kind of what you're needed. So what you would see here is that there's clearly a minimum right there. In fact, this is what's Kuchemann's really seeing as kind of some obvious cases where well within the Mach cone. So I'll draw that again. And so, if this is your Mach cone, right? And so this would be that beta. And I'll draw within that a vehicle in blue, okay? And I'm trying to highlight here the difference. So reminder, this would be S, and this length here is L. And then the Mach angle, to not use the same letters, let's call that X in of length, Y. And so when beta S over L is 1, again, the shock wave is touching. And so what's happening, showing here, is that really at these kind of, I'll just say supersonic conditions, most of these characteristics are going to show up at vehicles where the Mach number, or where the vehicle's far away from the shock. Now, I drew the shock. This is probably, for Mach 2, this is probably way too intense. Shock really should be a much smaller than I drew it. But we kind of see that. So Kuchemann also kind of lists out a couple different interesting configurations. So Mach number, and then I'll just say minimum drag coefficient. He does list that, and then beta S over L. So we can kind of think through it. And, a couple, 1.2, 2, and 5. Minimum drag coefficient here of 0.3, 0.15, and 0.05. And then beta S over L, 0.2, 0.35, and then 0.5. Right? And so this is really kind of showing that even kind of showing up at what we consider hypersonic speeds, that shock is starting to come in, and it's really saying like, no, like your minimum drag coefficient really is still within that shock wave. Now there may be other things at play, right? That would be for a given lift coefficient. And so if you can get enough lift coefficient with tiny wings, then maybe that's okay. But that actually might force you to be flying in lower atmospheres where at higher dynamic pressures, which would then drive a heat problem. So this is sort of not including effects of heat. Effects of heat might drive you at Mach 5 to a very different answer. And in fact, he'll talk about that almost straight up in the beginning of chapter 6. That'll be good to get to. And so really the drag coefficient then is now kind of complete. So we can write down really, as a reminder, this full thing. And so you have the drag due to friction, and then the full formula, 512 over pi. And then Kuchemann defines a couple terms so that there's some good similarity between designs. So this is the wave drag term, and tau is a volume term, and so it's the volume divided by the area to the 3/2. And then P is a planform term, and that's just the area over 2SL. So think of this as like it's a box, right? So planform area, again, if that's length, and since one side is S, this whole side is 2. And so if your planform area of half would look like that. Like it's basically, how much of this box are you taking up? And so this term here, I'll choose colors. This entire term here is the wave drag, the kind of the constant portion of the wave drag, the one that doesn't change with lift. And then you have plus looks like 1/2 lift coefficient squared. So the rest of this is changing with lift. So there's planform over S over L. And then there's their standard induced, that's a bracket. That's a standard induced vortex drag. And then KW is what he uses for a coefficient for the rest of the induced. And you get a beta squared, S over L squared in there. So this would be standard induced, and this is the sort of wave induced drag. And so that's a complete story, right? And so really you can start analyzing that. In fact, what you can do, you can even, it does this analysis for saying, hey, let's take tau equals 0. What does that mean? It means your wing is massive compared to your volume. So tau is 0 would be like a flying flat plate. And so if you took tau as 0, right, so you've zeroed out this term, and then you can actually take the derivative of the drag coefficient with respect to S over L and set it equal to 0, what you end up finding is that beta S over L is square root of KW over 2SL. All right, back. Had to take a quick phone call from the youngest. All right, so you can take the derivative of the drag coefficient compared to the the wing size, and then see how this compares. And yet you end up getting this KW over KV over K2KW. And basically, in the end, you end up seeing that beta S over L, you're going to want it to be less than basically square root of 2 over 2, so 707, right, for basically any kind of wave coefficient being greater than the viscous coefficient. So what does this mean? It means that for most configurations, you're going to want the shock wave far away, is what it comes down to. Far away from the vehicle. Now, it took me a little while to kind of chew on this, right? Is it because there's some like velocity curve or something that's going on? And the answer is, I think it's just more subtle than that. It's just that like for the given volume that you might be taking up for that aircraft, it's almost the drag being driven by the volume of that wing that's kind of going forward, right? And so it would just say that it's not worth it, even if you can get it tinier and tinier, it might not be worth it. Now, the piece that I don't quite understand, and we'll have to go kind of dig in, is like, this is sort of set for a given lift coefficient, and I think this is probably the wrong way to do it, right? You don't fix a lift coefficient. What you do is I have a weight of a vehicle, and I'm going to fix the lift. So given that I probably know, like, so let's walk through what you would know. I know the Mach number. Okay, great. And then for us, since we're flying at higher speeds, not this kind of Mach 2 business, so we'll write algorithm here. You would say Mach equals 4. Well, there's some engine reasons for 4. There's some temperature reasons for 4. Let's just say that we've kind of narrowed down that we think there's a sweet spot at 4, and then at every half Mach number above that, you start paying in terms of higher temperature materials cost. It doesn't necessarily help you with range. And if we're building things to maximize range, which commercially we are, then you would stay at 4. Now, military, you might have a reason to go 5 or 6, but that would be a military-driven problem, and you would sacrifice range for whatever that extra performance you're looking for. So Mach 4, you would then take this and you say, okay, I'm then going to choose an altitude, but I'm going to choose a temperature. So you would say temperature equals this on my vehicle. From that, you would then get a altitude. So from that altitude, I then now know at Mach 4, I now know my dynamic pressure, okay? So you've done that math. And so then, given, right, I would think not in terms of beta S over L, but I would make this diagram actually in terms of wing loading, because that's maybe a little bit how we're used to thinking about it, right? And so I know that lift is the dynamic pressure times the area times the lift coefficient, and I know that lift needs to equal to the weight at cruise, right? And so what you know is CL, right? That's the dynamic pressure, wing loading, right? So that's what you would know. So as you're varying wing loading for constant dynamic pressure, like this is what you're actually holding constant. So it's not CL equals 1. It would be, honestly, it would be some line of at this dynamic pressure, your wing, has to be basically so big. So given that, then what would you do to the shape of your wing? And so that's a little bit where Kuchemann did start thinking through kind of those configurations, because he kind of came up with a couple different ways you could do this, right? One, he said, okay, let's assume there's a vehicle that's got some sort of fuselage, and then I'll have some other kind of length of the wing compared to length of the vehicle, and then this would still be S. So that would be one configuration. There's another configuration where just if that's the shock wave, right, just pure delta wing. And then he actually did some thought experiments too on kind of the slewed wing, right? So there's your aircraft, and there's kind of slewed wing, and what that would look like. Actually, some pretty interesting things there. Interesting. There's kind of some aero things that look interesting, but one person has flown a slewed wing, and it's sort of compelling, but at the same time, not for other reasons. And honestly, it kind of walks through a range of configurations where this looks kind of interesting. And so, without kind of redrawing all of this stuff and going into maybe what amounts to be kind of maybe a little bit too much detail for the point of this lecture, we'll just kind of end with that. And this is what most recently we're seeing some studies that came out of SpaceWorks and others that are kind of driving towards an interesting point. The first one is that there really does seem to be a configuration at Mach 2. Okay, and some of this you have to go back to what are we looking for? If we're looking for range, remember range is again the heating value over G of our fuel. Again, kerosene, Jet A. If you put hydrogen in there, you better be accounting for the weight of the tank. It doesn't work out. And so really it's this sort of the total propulsive efficiency times L over D. That's the main one we're attacking here, right? This is sort of the main configuration we're interested in. And then, yes, 1 minus, and I'll write it like this, the propellant to get to cruise, and then the total propellant. So, any kind of advances in structural stuff, the advances here, you can lighten the weight of your vehicle structure. That'll help pack more fuel. but ultimately it's kind of this configuration here. And so what we're seeing is that around this Mach 2 configuration, there really is a very interesting thing, right? Kind of at this, like I said, beta S over L, pretty small, so kind of way away from the shock. And then we're seeing also now, also kind of this Mach equal 4 configuration. There's another sort of optimum there where this kind of works out. So I'll leave it there, and then we'll dig in a little bit more next time.